So today we want to introduce Labrador, and this is a work for with Harry, Kurt, Jeff, Juno, and we implement a part of Labrador protocol in the past week. Yeah, and I will briefly talk about the composition of Labrador from a high level. So yeah, enjoy. Okay, so first we want to decompose the name with this Labrador. So the whole name is the lattice-based recursively amortized demonstration of RNCS. So you can see first LB is like a lattice-based commitment. So in the original Labrador, we use the problem called MSIS for the hard problem. And so like the R-type commitment I introduced before 2 weeks ago. Yeah. Okay. And second is the recursively. So it's like a recursive proof composition inspired by bulletproof style. So the recursive compression method is based on an inner product argument. Okay. So, and third is the aggregate and amortizides. So aggregate is like, we know like the folding or something is called like use the random linear combination to aggregate some relation or some instance. So it's the same here. And amortized is used in Labrador is to split the witness. So into if you have a long or a big witness size, you can split it into the smaller parts. Okay, and the last one is the R1CS. In the Labrador, they call it a dot product constraint system, and in the paper they also has some like proof they can reduce the dot product constraint system reduced to R1CS. So what this means is you can if you can use the R1CS to implement like another program, so you also can use the DPCS to implement it. Okay, so this is a simple view to Labrador, what the component in. So in the low level is the algebra and some arithmetic. It's called the dot product constraint. Okay, and so they need some front end like Greyhound, Chihuahua, and some like they call this name to this arithmetic in their front end. Okay, and the second level is like some commitment scheme and Joylo projection, and Joylo projection is like to some benefit to the protocol, optimization for the protocol. Okay, and the random is the sampler, and the sampler in here is if you want to use the lattice-based cryptography, you need some sampler to how to generate some random number or random matrix. So it's important for lattice-based cryptography. And the top level is same as other snark or stark, so also have setup, proof, and verify. Okay, and so what relation in Labrador we want to prove is like this. So you can see it's this constraint we call the dot product constraint. So you can imagine it like the R1CS. So and this Si to Sj is like a witness, and so you can use some this matrix or some B or this parameter to make this equation is correct. Yeah, so it's more the same. I think it's almost like the RNCS. You can imagine it. Okay, and another constraint is a norm constraint, and this constraint is because if you use the lattice-based commitment scheme or lattice-based cryptography, you have to it has a parameter called non-bound, and so in here is the beta. So if you the beta is so big, the hard problem is have some easy to solve. So this bound is for security. So we want to like use some constraint to constraint this witness size to less than beta. Okay, so another, and then we want to two types of commitments in using Labrador. First is inner commitment, and inner commitment is just like outside commitment. You just to use the random matrix A and multiply to your witness, so you can get the TI. And but in here is some problems. It is if you send in latest commitment directly, it's very expensive. It's almost 4 kilobytes per commitment. So in this paper, they want to like hide this inner commitment into an outer commitment. So like we will use U. You can imagine it's like another outside commitment to to aggregate whole commitment in TI. Yeah, and okay, and the list things is the decomposition for this TI, and it makes the performance better. And the Jeff will explain this how to decomposition this vector. Okay, so another is aggregation, and aggregation is like the other aggregation system. So they use a random linear combination to combine this dot product constraint. Okay. Okay, and amortize. And amortization is over the witness vector. So this goal is like to consolidate the verification process instead of checking each constraint. So you can like combine it into some only one opening. So if you use the SI each other, you have to like opening every vector. But if you can use some challenge polynomials, you can combine it into Z, so you can just open it one time. Okay, and so jello projection is a component we used in this paper. So, okay, what? So nothing. Okay, so so you can the jello projection is certain like random linear maps from a high dimension to a low dimension space, and this projection advantage of using it is we can preserve the non-bound into the small constant. So it's how they do is like to send a random matrix and prove a sense projection and verify checks that. And this part that Juno explained to later. Okay. Yeah. And so we now let Jeff to explain how the decomposition do.
Thank you. Okay. So I'll use the whiteboard here. All right. So black one. Yes. Okay. So the prover will send the TI, which is A. This is a random matrix, and ASI. This is the input, which is a witness we are sending to. Prover want to send to verifier, and this kind of commitment is called outside commitment. And the reason why we are going to decompose those inner commitment is because it can compute more efficiently. Yeah. So I will talk about how to compose those Ti. All right. So Ti is a vector, and it is actually this. And we want to decompose it into this this form. So it becomes like Ti 0 and B1 0 at Ti 1 B1 square 1 and Ti 2 B1 square until all the way to T1. We have a constant number called T1 minus T1, and it can be computed like in the paper. It is like a constant. We can set it. T1 minus 1. So B1 is the basis of this form, and the T1 is also we kind of limit the length of this form. So that's why we need T1, and this can be computed, like you can check the paper and it has some formula to compute it, but this is kind of hard for me to understand. So I'll take an example for this. So Ti equals to 2, 6, 7. So let's say we have the Ti's like this, and every element inside it is actually a polynomial ring. You can just imagine this is just a polynomial now. And how to decompose this is we want to make it like this form. So maybe like we said B1 equals to 2. So we actually can maybe let's talk about this is T1, the first element. I will use this method 1 square and the coefficient, and this is the basis. And the coefficient is 1, 2, 3. So it is just like you can divide it into the form of binary. So you can do this thing 0, 0, and 0, 1, 0, 1, 1, 0. Right? So this is just the binary form of the decimal number. And we can actually consider this as another form, which is 1 equals to this 1, right? So 1x to 0, and at this. The 0 I'll just represent as 0. And this will be 2, 3. I'll just make it quicker. Sorry. 0, 1. And this is actually x, so we put x here, and 0, and 1x squared, 1x squared, 0. All right. So actually now we got a new polynomial here. So you can see if we separate if we divide it to a 0 here, we can actually get this. This is 1 plus 0 plus x squared to 0. And here we can also get 1 here, x plus x squared to 1. And this is 0. So now back to here. Our base is B1, and our base is 2 now. So we can get the base here, which is actually less. So now we can actually get the first element. We can divide it into this. And for all of this, we can actually, the ti0 is actually a form like, it's also a vector. So it will become like this. And this will be, we divided this into this form, and we just put the element here. Yeah. So that's how we get the decomposition of T1. Yeah. Thank you.
Okay, so I'm going to talk about JL projection. JL projection is a trick that you can do to project a data set to a smaller dimension and preserve the L2 norm, which is the Euclidean distance. So how it's done is it's using dot product. So we will have a random matrix A, and the dimension will be the target dimension. And times the original dimension. And then this random matrix, we will do dot products with our data. And the data will have the original dimension and times n. And the result of this dot product, we will get a C matrix with the target dimension and n. So that's like super simple. And how we get this matrix, we use Gaussian sample from in this paper. And yeah, I'm gonna show an example of how it looks like, and now I'm gonna talk about the mathematical proof behind it. So, and why this paper is using this is because we wanted to prove that a long witness has a short L2 norm, and instead of sending the whole witness to the verifier to check the L2 norm, we use JL projection to shrink the dimension down, so to ease the computation for the verifier. And because JL projection is very useful in data processing, it's also used in machine learning a lot. So this is a Jupyter notebook. I wrote it, and then using a scikit-learn package. How do I do it? Okay.
Could you enlarge the size?
Oh, yes.
Yeah.
Okay. Yeah, so what it's doing is it's taking a data from a data set that's having like 130K data, and then it's calculating the L2 norm, the Euclidean distance first before projection, and then it projects it to a lower dimension and then calculates the dimension, the Euclidean distance again. And this is how it looks like. So on this axis, this is the before projection. This is the projected, and this is the original space. But you can see like the distribution is almost x equals to y, so meaning like the distance is actually very close to each other before projection and then after projection. And it's not working, but okay. And this one is a graph of the rates. You can see it's almost at distance rate is almost at 1. And yeah, that's it. And this is the example I referenced from the scikit-learn documentation. Yep. And that's it for JL projection.
Then I will talk about some takeaways from the implementation of this protocol.
Where is it? Yeah. Is it here?这可以用。你跟我讲啊。
Okay. Yeah, although we didn't finish all the protocol, but I think that there are still, we only finished the first interaction between approver and verifier, and use some test data for the random data and parameters. But I think we still learned a lot. So I think this journey is a lot of fun, teamwork, and concrete learning because you are implementing it. You know what the structure, what the data means. So I'll go through the implementation process for us. So first we before the implementation, we have learned and discussed about the paper and this across the team members. We have whiteboard for us to understand what the paper is talking about. And then we take some notes. So this notes is from Juno to help us to understand and for the get the implementation. And next, we just put the paper and our code editor together to write the comments. You just write as many comments as you can because it's a very abstract math object. And you need to understand what the parameter, each parameter means, how you can get them. So we just write the comments. And then such as for this example, if you don't know, you just make some examples such as this data structure. It's very complex. This is just T0. Actually, T have more complex data than this. You have example data, then it will help you to code. Okay, such as this this B. Okay, no B. We have R-type commitment. So there is a B matrix. So B matrix is this candidate structure, and if you expand it, it's like this. If you just read the code, it will be cause bugs very easy. So I just use some sample data to help me think and implement. Then is teamwork. We use this big TV and all of us to code together to read the comments and figure out how the parameters work. So during this, there are a lot of discussions. Okay, and then the next is the, yeah, you can continue to build wherever and wherever possible. Yeah, it's also teamwork. So the takeaway is that for paper, you just learn and discuss, and read comments as many as you can, and then you do the implementation. You read concrete code. Tests are really important for that, and I think from concrete to abstract, if you just do the refactoring, after you do many rounds of refactoring, your code will become abstract, I think. And finally is teamwork. And our GitHub link is here. You can follow us. If you want to contribute, you can let me know. Okay? Give me a star.